In part 2 of Everything You Never Wanted to Know About Statistics, we discussed the confidence interval. A confidence interval is a range of values within which we expect the population parameter to fall. In this section, or in this video, instead of creating a range of values for the population parameter, we use a process to test the validity of a statement about the population parameter, and we call it a hypothesis test. So what exactly is a hypothesis test? Well, maybe we should start with first, what is a hypothesis? So a hypothesis is really just a statement or conjecture. We're speculating about a population of interest, and we do that based off of the sample that we have, but we're speculating about a population of interest, and it's developed for the purpose of testing. Now that we know what a hypothesis is, what's the hypothesis test? Okay, hypothesis test is a procedure based on sample evidence and probability theory to determine whether the hypothesis is a reasonable statement. Let's break that down a little bit more simply. What we're going to do with a hypothesis test is we're going to say originally that there's nothing going on. Everything is normal, everything is great, and we want to nullify that. That's what's called our null hypothesis. We want to nullify that. We want to say that we think something is going on, or how likely is it that something is going on. So a null hypothesis is a statement about the value of a population parameter developed for the purpose of testing. The statement's assumed to be true unless sufficient evidence from sample data shows that it is false. So in other words, again, the null hypothesis is what we're trying to nullify. And the way to think about that is to think about it as the null hypothesis is when we think that nothing is going on, and we're trying to say that we think something is going on, which leads us to our alternate hypothesis. And the alternate hypothesis is a statement that is accepted if the sample data provides sufficient evidence that the null hypothesis is false. The steps that we use to do null hypothesis testing are: first, we state the null and the alternate hypothesis. Then we select the level of significance, and we're going to get into each of these there. The level of significance is the level of risk that we're willing to accept of rejecting a null hypothesis that's really true. That's called a type 1 error. Step 3 is we identify the test statistic. We formulate a decision rule. In other words, we're saying we want to try to nullify this. At what point is it that we would nullify this? In other words, when we would reject the null hypothesis, the null is right here, reject the null hypothesis, at what point would we reject the null hypothesis and accept the alternate hypothesis? That's what we're doing here. We're creating that decision rule. And then here we take a sample, we calculate a sample statistic, and we arrive at a decision that's either do not reject the null hypothesis or reject the null hypothesis and accept the alternate hypothesis. Another way that I like to look at this, it makes it a little bit more understandable for me, is in the first case we assume that nothing is going on. That's our null hypothesis. Then we look at our alternate hypothesis, which is what do you expect to get if something is going on? And then the third is, as I said, here in this guide it's step 2, but in the example I'm using, step 3 is how much risk of rejecting the true null hypothesis are we willing to accept. And we'll talk more about that as we go. And then we'll go take our one little sample. We'll say, what do we actually get in our one little sample? We say, how likely was it that you got what you got? And if it's very unlikely, we'll call baloney on the assumption that nothing is going on. There's some things that you'll want to make note of about the null and alternate hypotheses, and we're going to go ahead and just cover this entire process over the course of this video. H sub 0 is an indicator of the null hypothesis, and that's pretty universal regardless of what textbook you're looking at. H sub A or H sub 1 are your alternate hypotheses, and some books will show H sub A and H sub 1, and there's more significance to H sub 1 later that we'll talk about perhaps a little bit later, but not in this video. H sub 0 and H sub 1 are mutually exclusive and collectively exhaustive. So most people have heard of mutually exclusive. That means that if one event is occurring, the other event cannot occur at the same time. So if you have H sub 0, or the null hypothesis is occurring, you can't have the alternate hypothesis occur. And if you have the alternate hypothesis occur, you can't have the null hypothesis occur. But collectively exhaustive means it includes every possible option between the two. So the point is not so much that these are already like that, it's when we create our null and our alternate hypothesis that we have to ensure that they are mutually exclusive and collectively exhaustive. And the null hypothesis is always presumed to be true, and the alternate is the one that's trying to nullify the null hypothesis. In other words, the burden of proof is on the alternate hypothesis. And we always reject, or we fail to reject, the null hypothesis. We never accept the null hypothesis, because in order for us to accept the null hypothesis, we would have to have the entire population data, which we don't. We're taking a sample. When we create the null and alternate hypotheses, the equal sign, or the equality, always goes with a part of the null hypothesis. So you'll have either an equals, or a greater than or equals, or a less than or equals, and that will be part of the null hypothesis. And again, I want to emphasize that we never accept the null hypothesis. If we conclude that we do not reject the null hypothesis, that does not necessarily mean that the null hypothesis is true. It only suggests that there is not sufficient evidence to reject the null hypothesis. Rejecting the null hypothesis then suggests that the alternate hypothesis may be true. And again, to prove without a doubt that the null hypothesis is true, we would need all the population data. The null hypothesis always gets the equal sign because the null is the statement we are testing, and we need a specific value in our calculations. We only turn to the alternate if the null is rejected. And our choices are to reject the null or do not reject the null. What if we come to the wrong conclusion? That's where we talk about different types of decisions and errors that you can come up with in hypothesis testing. So if the null is true, the real null is true, and the researcher does not reject the null, that's the correct decision. That's what we want to get at. Or we want to find out if the null is false, then we want to reject the null hypothesis. And a type 1 error is when we reject the null hypothesis. So we've rejected the null hypothesis, but it's actually true. Now the type 2 error is when we do not reject the null when the null is not true, and you can kind of think of it as a not rule. In other words, we do not reject and it is not true. The null is not true. When we look at the type 1 error, it's looked using the Greek letter alpha, and it's also known as the significance level or the alpha level of a test. The type 2 is denoted by the Greek letter beta. We'll discuss these types of errors again later. For now, let's look at setting up a hypothesis. So when we set up our null hypothesis, the status quo is what is the null hypothesis. In other words, when we assume that nothing is going on, that's what we put in as the null hypothesis. What we're trying to do is to prove, or what we're trying to prove is set up as the alternate. So in other words, that's what we think is going on, and that's what we set up as the what we expect to get if something is going on. And remember that the alternate hypothesis has the burden of proof. So when we're doing the problem solving, when we're doing this in the real world, we have to look at keywords to kind of get an idea of what they mean in the form of a symbol. So some keywords that you can look at are right here: improved, better than, as effective as, different from, has changed, etc. So when you see words like larger or more than, your inequality symbol is greater than. For smaller or less than, you have the inequality symbol is a less than symbol. When you hear things like no more than, you use a less than or equals sign. At least means greater than or equal sign. And you can go down this table yourself. We'll talk more about it, but think of the null as what you expect if nothing is going on. The alternate as what do you expect to get if something is going on. Remember too that you might see h sub a or h sub 1 because they're interchangeable for our purposes. There are one-tailed hypotheses tests and two-tailed hypotheses tests, and those tails are referring to the distributions. So a two-tailed test, for example, is an indication of here, and we set up these boundaries and we look at the rejection regions. And for this, when we're translating words, we can say if it's different from, that means it just could be greater than or it could be less than. So that's when we indicate a two-tailed test. And so we have the one-tailed tests and over here. The one-tailed tests are also considered directional tests, more than or less than. For example, the top right diagram depicts a left-tailed test. The null hypothesis, in other words, is that the mu is, which is the population mean, is greater than or equal to some value that equates to a negative 1.65 z value. And the alternate value is that the mu is some value that equates to less than negative 1.65 z score. So what you have here is the critical value. That's your boundary or your cut line. So what we're going to say is, in this case here, if we pull our one little sample and we get a value that ends up over in this area here, we're going to say that's pretty unlikely. We're going to call baloney on the null hypothesis that nothing is going on. Likewise, in the two-tailed test here, if we get our sample statistic, we pull our sample, we calculate the sample statistic, and the value comes up to either here or here, we're going to call baloney on the assumption that nothing is going on, and we're going to say that yes, there is a difference. So let's look a little bit at the distinction between a test statistic and a critical value. Again, I've used both of those terms. The critical value is what establishes the boundary beyond which, or more extreme than, you consider it to be unusual or not likely due to chance, or baloney is where you'd call baloney. So if it's very unlikely, we would call, in other words, it would show up in here, it's very unlikely that would occur, and we would call baloney. So again, that's the critical value that we calculate ahead of time based on the level of risk of rejecting a true null hypothesis when in fact it's true, that we determine ahead of time. So we calculate that. And then the test statistic is what we calculate based off of a sample that we select. So if we take a sample, take a bunch of sample observations, and we calculate a test statistic, and we find out where it fits on our distribution. And if it's anywhere in the shaded area, it's too extreme for us to believe that this was just a chance occurrence, so we call baloney on the null hypothesis and we reject it. Again, the test statistic, that's a value that we determine from sample information. It's used to determine whether to reject the null hypothesis. And it can be a z score, a t score, an f test statistic, or a chi-squared test statistic. Again, this is all based on sample data that we pull. And the critical value, that's the dividing point between the region where the null hypothesis is rejected and the region where it is not rejected. And usually it's indicated something along the lines of z sub CV for critical value, or any of the other tests like that. We mentioned that we are testing to see if we should reject the null. Let's look at what that means. In this example, we have an alpha, our level of significance, of 0.05. Because this is a two-tailed test, we divide the rejection region evenly between both tails, which puts us at a 0.025 level of significance on either side. If the test statistic, the z-test, for this falls in the rejection region, then we reject the null. So these are the rejection regions here. That actual line on the 1.96, that's our critical value. That's our cut line. That's our boundary. If we get a test statistic anywhere inside of here, then we say, oh, that's quite possible that it's happened due to chance, so we will not reject. Let's look at the steps of testing a hypothesis again. So step one, we state the null hypothesis and the alternate hypothesis. And the other way to look at that is, with the null hypothesis is where we assume nothing is going on. The alternate hypothesis is, what do you expect to get if something in fact is going on? And then step two, we select a level of significance or probability of rejecting the null hypothesis. And as we did with the confidence level for the confidence interval, this is based on our expertise or the traditions of our discipline. So if you're inexperienced, you don't know exactly what significance level to use or alpha level to use, you can go to your literature and see what others are using, and that can give you at least some idea. The traditional levels of significance that are used are 0.05, 0.01, and 0.1. Those are traditionally the ones you see most often. So step three, we determine which statistical test to use, and that's going to be based on the type of analysis we're going to perform. And before I flip the slide, again, the level of significance is how much risk of a type 1 error, the probability of rejecting the null when in fact it's true, are you willing to accept. So how much risk of a type 1 error are you willing to accept? Step four, we formulate the decision criteria. Again, that goes back to our cut lines here. And we're going to say, if it goes outside of the cut lines, outside of the critical values, or it's more extreme than the critical values, then we're going to go ahead and say that's where we're going to reject in the terms of the process. We're going to also say that's where you call baloney. So then we state the decision rule for when to reject the null hypothesis. And then in step five, we go ahead and we evaluate the sample statistic against the critical values, and then we reject the null or accept and accept the alternate, or fail to reject the null hypothesis, and we interpret our results. So in these two steps, what we're doing is we're establishing our boundaries. Then we go ahead and say, what do you actually get on your one little sample? How likely is it that you got what you got? If it's very unlikely, in other words, it's in the rejection regions, you call baloney on the assumption that nothing is going on, the null hypothesis. And then you interpret the results, of course. So we can use this hypothesis testing to test the sample mean against the population mean. So we want to test the hypothesis that the sample is from the same population when the population mean is known. And so we're going to use the z-test or the t-test. We use the z-test using the z distribution when the sample size is large, greater than 30, or the population standard deviation is known. This you should remember from our confidence interval video. And we use the t-test or the t distribution when our sample size is small, 30 or less, and we don't know the population standard deviation. To use the z-test or t-test, the variable must be at least an interval level of measurement and normally distributed. So here are some possible null and alternate hypotheses statements that we would have, and our decision rule. So in this case, our null hypothesis, we'd say that the mu is equal to some value, and the alternate is that the mu is not equal to some value. And then we reject the null hypothesis, and this is just saying, because it's a two-tailed test, we're just saying that the absolute value of z is greater than the z critical value. So this is another way to write the critical value that you might see. The other way you could write this is you reject the null hypothesis if z is the positive z is greater than the z critical value, and or that is the negative z is less than the negative z critical value. This is just an easier way to show it. So this would be the way you could show the z as being less than the negative z critical value. And again, we'll go through one of these examples and you'll see how it all works out. But if you remember, the equality symbol goes with the null hypothesis, and that's the way we have each of these indicated here. And this is just your formula for the t-test statistic that we would calculate based off of our sample data. And here's the z-test statistic that we would use based off of our sample data. Let's have a quick review of probability. Okay, moving along. Now, as a reminder, we want to calculate the test statistic, and we're going to compare that test statistic against the critical values to see if it's more extreme or on the outside of the critical value. So the way we do that is we find the difference between the sample mean and the known population mean, and then we find the z statistic. And we use these calculations. These are our test statistics. Okay, now it's time for fun. Let's go through an exercise. Here's our scenario. We have the Jamestown Steel Company manufactures and assembles desks and other equipment. The weekly production of the Model A325 desk at the Fredonia plant follows the normal probability distribution with a mean of 200 and a standard deviation of 16. Why are these underlined? Well, by now you should recognize that I'm giving you a little bit of help and pointing out that we're going to be using those values later in our calculations. So we've recently introduced new production methods and new employees have been hired. So the Vice President of Manufacturing would like to investigate whether there has been a change in the weekly production of the Model A325 desk. A sample of the last 50 weeks yields a sample mean of 203.5 desks. Use the 0.01 level of significance. So has there been a change in the weekly production? Why is change underlined? Well, that's to give you an indication of what type of test we're going to do. So if there's going to be a change, we're seeing if there's a difference, which means that there's going to be a two-tailed step. Do you remember what the first step of the null hypothesis was, or is? Well, before we get to that, notice that we know the population mean of 200 and the population standard deviation is 16. So we know the population mean and standard deviation. So what type of test statistic can we use? We're going to use the z-test statistic. So let's go and look at step 1. You should have remembered by now that step 1 is to state the null hypothesis and the alternate hypothesis. In our example, the null hypothesis is that the mu is equal to 200. The mean weekly production is not different from 200 desks per week. The alternate is that the mean weekly production is different from 200 desks per week. So we assume nothing is going on, that the mean weekly production is not different from 200 desks per week. The alternate is, what do we expect to get if something in fact is going on? And then what level of risk of type 1 error are we willing to accept? Well, that's a given in this problem, so we're willing to accept a 0.01 level of risk. Our alpha level is 0.01 as stated in the problem. The next step that we do is determine which statistical test to use. Well, because we know the population standard deviation and we know the population mean, we can use the z-test statistic. So we have our z-test statistic down here. And let's move to the next step. Formulate the decision criteria, or the decision rule. So based on the null or the alternate hypothesis that the mu is equal to 200, we're going to reject the null hypothesis if the absolute value of z, remember it's a two-tailed test, so if the absolute value is greater than the z critical value, so the absolute value of our z-test statistic, if it exceeds the z critical value, then we're going to reject the null hypothesis and call baloney on the assumption that nothing is going on. Since our alpha is equal to 0.01, our z critical value is equal to 0.005. The area between the tails, that means this white or lightly shaded area, is 0.99. The rejection area is based on, we take the 0.5 and we subtract negative 0.005 and we get 0.4950, and that has to do with the way that our book calculates the probability rates in our probability distributions. So another way to look at our decision rule is that we're going to reject the null hypothesis if it's not between negative 2.58 and positive 2.58. So in step 5, what we do is we actually take our one little sample and we calculate what it is that we actually got in our one little sample, and we make a decision and interpret. So we now calculate our test statistic. Now remember, this is our test statistic based off of our one little sample of data that we collected. It has nothing to do with the critical value per se. The critical value is a different calculation, and the critical value is already established on our probability distribution. So this is all based off our sample data, and we're going to say that if the z is greater than the z critical, or excuse me, the absolute value of the z is greater than our z critical value of 2.58, in other words, if it's in this rejection region or this rejection region, we're going to reject the null hypothesis. So we calculate out our test statistic based off of our one sample that we collected, and we find that our test statistic is 1.55. It's not greater than 2.58. Because 1.55 does not fall into either rejection region, it's over here, we fail to reject the null hypothesis. Our interpretation is that, or our conclusion is, that the population mean is not significantly different from 200. So we would report to the Vice President of Manufacturing that the sample evidence does not show that the production rate at the plant has changed from 200 per week. Let's compare the rejection region of the one and two-tailed tests. Remember, when we did the two-tailed test, we had to split the amount. The 0.01 we split between the two tails. So each of those tails is half the size of the rejection region if it's all on one tail. So it's greater over here. The rejection region is larger if we had it as a one-tailed test. So can we conclude, because of the improved production methods, that the mean number of desks assembled in the last 50 weeks was more than 200? Remember, our computed z-test statistic was 1.55. It's still in the do not reject region, which is right in here. So the sample evidence does not show that the mean number of desks assembled is greater than 200. So, are we done? No, because what do we do if we don't know the population standard deviation and we have a small sample? When we don't know the population standard deviation, the sample standard deviation is used in its place. We use the t-test statistic. The t-distribution is used for the test statistic, which is computed using this formula right here, which is very similar to the z-statistic. And it's similar to what we're doing with the confidence intervals. The next scenario we're going to go over is about insurance. So you can read this here, but essentially the insurance company reports that the mean cost to process a claim is $60. And industry comparison shows that to be larger than most other insurance companies, so the company is trying some cost-cutting measures. To evaluate the effect of the cost-cutting measures, the supervisor of the claims department selected a random sample of 26 claims processed last month. The sample information is reported below. At the 0.01 significance level, is it reasonable to conclude that the mean cost to process a claim is now less than $60? Now I know some of you are probably thinking, well, why didn't he just take 4 more and we could use a z-test? Well, then that would mean I'd have to go find a different scenario. So this is the scenario we'll stick with, and we'll stick with 26 claims. Here are all of the 26 claims. Sample mean is $56.42, and the sample standard deviation is $10.04. Now that's not given in the scenario. That's based off of these calculations here that I'm not going to go through because we've gone through that in other videos. If you want to calculate the sample mean and standard deviation for those, feel free to do that. So what test statistic should we use? Well, since it already says t-test example up there, you should be able to figure out that it's a t-test example. But Really, we should be able to figure out that it's a t-test example even without that, because we have only 26 claims and we don't know the population standard deviation. What's step 1 again? State the null and the alternate hypotheses. So we assume that nothing is going on. The mean population is greater than or equal to $60. The alternate is what do we expect to get if we think something is going on, and we would expect that the population mean is less than $60, or the population mean cost to process a claim is less than $60. Step 2 is we select the level of significance using all of our expertise, which in this case our expertise was provided for us in the scenario, and so we're looking at the level of risk of a type 1 error, in other words, the probability of rejecting the null hypothesis when in fact it is true. That's the level of risk that we're willing to accept, 0.01. Then in step 3, we determine which statistical test to use. We did that on the previous slide already. We use the one sample t-test since our population standard deviation is unknown, and our n is less than or equal to 30, and our testing is against the known population mean. Again, in test 4, we're going to formulate the decision criteria. So how do we formulate the decision criteria? We set up a boundary or boundaries, and beyond those boundaries are where we're going to reject the null hypothesis. Based on an alternate hypothesis of the mu is less than 60, we're going to reject the null hypothesis if our t-test statistic, what we get with our one little sample, is less than or equal to our t-critical value. Then we're going to reject the null hypothesis. So we have our shaded area here. If our test statistic from our little sample comes out to be in here, that's where we're going to reject. Since alpha is 0.01 in the left tail, then this is where we put our critical value, negative 2.485. The area above the rejection is 99% of the probability distribution, so all this area here. So our rejection area based on the critical value in table A2 is that it's a one-tail test at alpha of 0.01, and the degrees of freedom is 25, n minus 1. So our t critical value is negative 2.49, or more precisely negative 2.485. We're going to reject the null hypothesis if the t value is less than our negative 2.49. And we can find that critical value in table A2. I've already provided it here, but you can go to table A2 on page 893. You go to the one-tailed test column, look for 0.01. You go down to the degrees of freedom row of 25, and you go where they intersect, and you find that it's equal to negative 2.49. So here's that table, or actually just a little screenshot of that table. And you go down, as I said, it's a one-tailed test, 0.01, and you go down to the degrees of freedom line, and you go where they intersect, and you get 2.49. But based on what the scenario gave us, we know that it's a negative that we're looking for. Finally, we go to step 5. We make a decision and interpret the result. Well, how do we make the decision? Well, we collect our one little sample. We look at our test statistic, which is our t-test statistic here. We then look at how likely is it that we got what we got. In other words, we compare it to our rejection region, and we say, if it's very unlikely, we're going to call baloney on the assumption that nothing is going on, the null hypothesis, in other words. And so we have negative 1.818 is not less than negative 2.485. It's over here. It's in the do not reject area. And so then we interpret it, and we say because negative 1.818 does not fall in the rejection region, the null is not rejected at the 0.01 significance level. We have not demonstrated that the cost-cutting measures reduce the mean cost per claim to less than $60. The difference of $3.58 is between the sample. The difference between the sample of $3.58. The difference. Let's try this one more time. The difference of $3.58 between the sample mean and the population mean could be due to sampling error. Let's take another look at our error types. Remember, the type 1 error that occurs when we believe that there is a genuine effect in our population when in fact there isn't. So that's when we reject the null hypothesis when in fact the null hypothesis is true. In other words, we shouldn't be rejecting it. The probability is the alpha level, and that's usually 0.05, 0.01, or 0.1. And then the type 2 error occurs when we believe that there is no effect in the population when in reality there is. Remember, that's the not rule, meaning it's not true and we should not reject the null hypothesis. The probability of this occurrence is the beta level, and it's often 0.2. And here's another reference chart for the type 1 and type 2 right here. Let's back up a second. Here's a reference page that you can keep. And these are different terms. And another reference page here. Type 2 is when we do not reject the null hypothesis when the null is not true, the not rule. Another way to do the hypothesis testing is to use the p-value instead of the critical values, and that's becoming more the norm because our statistical software can calculate the p-value for us. And the p-value is the probability of observing a sample value as extreme as or more extreme than the value observed given that the null hypothesis is true. This is tied to the t-test in the sample. And the good way to remember this is when we're testing a hypothesis using the p-value level, when we will reject the null hypothesis when the p-value is less than the significance level. Remember, we've chosen the significance level. So if we get a p-value that's 0.03, and before we started we chose the level of 0.05 for our significance level, our p-value is lower than our significance level, so we reject the null hypothesis. An easy way to remember this is if the p-value is low, the null must go. And by that we're saying if the p-value is lower than the significance level, the null must go. Let's look at the t-distribution table on page 893 for the p-value. So in the last problem we used the 0.01 level of significance. Here for this example we're going to use a 0.05 alpha level of significance, so don't be surprised if we get a different result. And in the last problem the hypotheses were that the mu is greater than or equal to 60 for the null hypothesis, and the alternate was that the mu was less than 60. And we were going to reject the null hypothesis if the t-value is less than or equal to our t-test statistic, to be more specific, is less than or equal to our negative t critical value. And we set up our decision rule that we're going to reject the null hypothesis, as I said, if the t is lower than the t critical value, and where we have our t is test statistic is equal to negative 1.818, and our t critical value is negative 1.708 at if we did this at a 0.5 level, and we did it when we did it on our prior example, it was negative 2.485, I believe. So if we did this the t-critical value method, then we would reject the null hypothesis if we did it at the 0.05 level, because our t-test statistic would be the same, negative 1.818. That was what we got off of our one little sample, but our t-critical value changed because we changed our alpha level. So we can also use the p-value, and in our p-value approach we're going to have the decision rule that we always have, which is we're going to reject the null hypothesis if the p-value is lower than the alpha. So if the p is low, the null must go. So how do we determine the p-value? Well, one option is to use our textbook. We can turn to table A2 on page 893 of our book. And we aren't actually able to calculate an exact p-value from the table, but the best bet we can come up with is that it's somewhere between the values that we find in the 0.01 column and the 0.05 column. And we go down to the 25 degrees of freedom area, and we find that the value for 0.05 is 1.71, and the value for 0.01 of the one-tailed test is 2.49. So by seeing that we have a range of 1.71 and 2.49, our 1.818 actually falls within there. So the best we can do is say that our significance, or p-value, is between 0.01 and 0.05. Doesn't really help us much when we're trying to see about rejecting. Our decision rule is to reject it if the p-value is less than our alpha, and our alpha is 0.05. So option B is to go into Megastat, and we can calculate our p-value in Megastat, and we come out with a 0.0405. Since the 0.0405 is lower than the 0.05, then we reject the null hypothesis at the 0.05 significance level. The p is low, so the null must go. And we accept the alternate hypothesis that the mean cost per claim is less than $60 after the cost-cutting measures were implemented. So let's do a comparison with a little bit of detail between the test statistic approach and the p-value approach. For the test statistic approach, it depends on the directionality of the hypothesis. Of course, if we have the absolute value of the test statistic is greater than the critical value when we're using a two-tailed test, then we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. And then here are our two one-tailed test possibilities as well. However, on the p-value approach, the decision-making is always if the p is low, the null must go. So if the p is less than the alpha significance level, then we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. We can look at the different approaches graphically right here. When we use the test statistic approach, we're going to compare the t-test to the t-critical value. Now this also could be a z-test or another type of test. But what we do is we establish our boundary, or our critical value, beyond which we believe any of this is, the likelihood is too unlikely to have occurred by normal occurrences or by chance. We think something is going on. That's our region of rejection. And in this particular graphic, it's based off of the 0.01 significance level, the alpha level that we've chosen. And in the p-value, what we do is we compare our p-value to that alpha level instead. And if the p-value is low, or in essence lower than the alpha level, then we reject the null hypothesis. So for the p-value approach, we first calculate the test statistic value. We calculate the probability of finding that test value or a value that is more extreme, which is our p-value, and we compare the p-value to the significance level that we have chosen a priori, which is Latin for doing it beforehand. So if the p-value is low, the null must go. We reject the null hypothesis. And for the test statistic approach, we calculate a critical value, which is really just the z or t value of our chosen significance level. And then we compare the test statistic of our sample observation against the critical value. If our test statistic is outside the critical value, in other words, it's in the rejection region, we reject the null hypothesis. There are some concerns with null hypothesis significance testing, or weaknesses that might be considered part of a null hypothesis significance test. So we'll see those by asking the question, what is the statistical significance? And that stands for null hypothesis significance test. Tell us. Does it tell us the importance of an effect? No, it just tells us the significance depends on the sample size. Does it tell us that the null hypothesis is false? No, we always look at it as though it's false. And then does it tell us that the null hypothesis is true? No, it's never true. And another problem with null hypothesis significance testing is that it encourages all or nothing thinking. In other words, you either are good or you're not good. So we still teach null hypothesis significance testing because it comes into play with a lot of the calculations and analyses that we do, but it seems that a lot of the community is moving towards using confidence intervals because it provides a little more information than a null hypothesis significance test does. And that concludes this video. I hope it's been of help to you, and I hope you have a great day.